this is Mrs. Often with another video on parallel lines and special angles. This video deals with proving that two lines or more lines are parallel. So the objective for this lesson is to use the angles formed by a transversal to prove that two lines are parallel, or to calculate the value of a variable that would make two lines parallel. This video is a little bit longer, so grab yourself a drink and a snack and get settled in to do some proofs. Now we want to remember that the converse of a theorem is found by exchanging the hypothesis and conclusion, that is, swapping the if part with the then part. It's not automatically true, but if it is true, it's stated as a postulate or proved as a separate theorem. So our first postulate is the same side interior supplementary postulate. If two coplanar lines are cut by a transversal so that a pair of same side interior angles are supplementary, then the two lines are parallel. Our hypothesis is if these two angles have measures that sum to 180, the conclusion is then lines M and N are parallel. Now notice we're abbreviating this with the P at the end because we are starting with the two angles being supplementary and using that to prove that the lines are parallel. Let's see this in action using the converse of the same side interior angles postulate. We want to find the value of x that makes line L parallel to line M. We are given that the measure of angle 3 is 4x minus 10 degrees and the measure of angle 5 is 3x minus 20 degrees. Now, if these two lines, L and M, are to be parallel, measure of angle 3 plus measure of angle 5 must be 180. So let's go ahead and add those together. And by using some algebra, we determined that x is equal to 30. A postulate that is pretty well known in geometry is that through a point P, not on line L, there is exactly one line that is parallel to line L. Now this is true in Euclidean geometry. It guarantees that for any line L, you can always construct a parallel line. In other types of geometry, non-Euclidean geometries, you can construct no parallel lines, or you are able to construct an infinite number of parallel lines. Fortunately for us, right now we're just dealing with ideas of Euclidean geometry. If you want to learn more about non-Euclidean geometry, ask me in class, and I will be happy to point you in the direction of some resources. We have some converses of our other theorems here. The alternate interior angles theorem. The converse of that can be used to prove two lines parallel. We can use the converse of the alternate exterior angles theorem to prove two lines parallel. And we can use the converse of the corresponding angles theorem. So all of these are just saying if the angles are congruent, then the two lines are parallel. And we want to have a pair of angles that are one of our special pairs, or we want to be able to get to that point. And then we can prove that two lines are parallel. All right, let's look at proving one of these theorems. Let's prove the alternate interior angles theorem. We're given that angle 2 is congruent to angle 6, and we want to prove that R is parallel to S. We'll start with angle 2 being congruent to angle 6. That is, of course, given. Now, by the definition of congruent, we have the measure of angle 2 is equal to the measure of angle 6. 2 and 7 are supplementary, and 3 and 6 are also supplementary because they are linear pairs, as seen in the diagram, and the linear pair theorem tells us this. This means that the measure of angle 2 is equal to, or plus the measure of angle 7 is equal to 180. We also know that because 2 and 7 are supplementary, and 3 and 6 are supplementary, and 2 is congruent to 6, by the congruent supplements theorem, angle 3 must be congruent to angle 7. Therefore, the measure of angle 3 is equal to the measure of angle 7. So we have now that the measure of angle 2 plus the measure of angle 3, just substituting what we had back here in number 4, by substitution, measure of angle 2 plus measure of angle 3 is 180 degrees. And this leads us to, because of the same side interior angles supplementary postulate, the fact that R must be parallel to S. So let's look at this diagram. And we can use the AIP theorem to determine the value of x that makes R parallel to S, and then find the measure of angle 3. Well, we notice that 3 and 7 are alternate interior angles, so they must be equal to each other. Setting them equal to each other and using algebra gives us 2x equals 44, or x equals 22, and then we can use substitution to find the measure of angle 3. Angle 3 from the diagram looks like an obtuse angle, but we do want to make sure that we check and get that measure. The measure of angle 3 is 108 degrees. Remember, you can pause the video at any time to work this stuff out for yourself. All right, another example, proving lines parallel. We are given that P is parallel to R, and angle 1 is congruent to angle 3. So we're going to see these statements and reasons pop up. P is parallel to R is our given. Because of that, angle 3 is congruent to angle 2 by the alternate exterior angles theorem. 1 is congruent to 3 is another given. By the transitive property of congruence, then, we have 1 is congruent to 2. And this leads us on the converse of corresponding angles theorem to come up with L is parallel to M. Here we have angle 1 is congruent to angle 4, and angles 3 and 4 are supplementary. Now, just a quick notice here, as you make your plan for proof, you might want to notice to yourself 2 and 3 are vertical angles. So that tells me they are going to be congruent. And where I have some pairs here, I see that 3 and 4 are supplementary. That's a given. So I'm going to end up using that and SSISP to prove that M is parallel to N. And then I can work my way back, again using same side interior supplementary postulate to show that L is parallel to M. So let's get started with that on our next slide. We have angle 1 congruent to angle 4 is our given. So the measure of angle 1 is equal to the measure of angle 4 by the definition of congruent angles. Angle 3 and angle 4 are supplementary as a given. So that means that their measures sum to 180. And notice that's in 2 steps. We also have that the measure of angle 3 plus the measure of angle 1 is 180 degrees. That's substitution. By the vertical angles theorem, I have that the measure of angle 2 is equal to the measure of angle 3. Further substitution gets me that the measure of angle 2 plus the measure of angle 1 is 180 degrees. I can say that they are supplementary then by the definition of supplementary angles, and that by the converse of same side interior angles, L is parallel to M. Now, let's look at this. Here's an example. Suppose the corresponding angles on the opposite side of the boat measure 4y minus 2 and 3y plus 6. So that's my angles 1 and 2 here. They are corresponding angles. What value of y will make the angles congruent? Well, I want these angles to be equal to each other. So I'll write the equation 4y minus 2 equals 3y plus 6. This should be pretty quick to solve. You may even be able to solve it by inspection. Let's check this out and see what answer we get. Here's our equation, and here is our solution. Y equals 8 is the value that will make the angles congruent. Now the oars are also parallel by the converse of the corresponding angles. Please be sure that you can do the problems in this lesson quiz to check your understanding. This is really all about being able to identify the special angle pairs. So if 4 is congruent to 5, what special angle pair is that? 2 is congruent to 7. 3 is congruent to 7. And if 3 and 5 are supplementary. So there's 4 questions. 4 congruent to 5. 2 congruent to 7. 3 congruent to 7. And that the measure of angle 3 plus the measure of angle 5 equals 180 degrees. Thanks so much for joining me, and make sure to keep studying your math.